Hi, and welcome to this quick look at acyl chloride reactions. So rather than list all the different things that acyl chlorides react with and therefore all the different products they can make, I'm going to try to explain what the commonality is between all of them. So if you understand the pattern underneath it all, you can then apply this across to unusual looking compounds by looking for certain structures that are present. So here's a few of the functional groups that are made when acyl chlorides react. You've obviously got an ester there. A phenol ester is a normal ester, but it's got a benzene ring attached to the oxygen. So instead of R with a little apostrophe next to it, you've got a benzene ring. This particular example would be called phenyl ethanoate. Now you've got different types of amides, which I'll talk about in a moment, but this particular one is a primary amide. And then you've obviously got carboxylic acids. So although this video isn't really about amides, I'm just going to quickly introduce them. You can see what they've got in common. They've got a CO double bond, just like an acyl chloride has a CO double bond. So essentially this would be the part that comes from the original acyl chloride. So we need to think about what is reacted with it. In this case, it would be ammonia. This would be a primary amine. This would have been a secondary amine. Now, again, this video isn't really about amines. You might be watching this knowing a little bit about amines already, but I'm designing this video for people who haven't come across amines or amides yet. So I'm just making a passing mention of them here. So here's some of the reactions that acyl chlorides undergo. So I'm hoping what you're seeing as I reveal them is the acyl chloride functional group is basically this bit at the left. So what we're trying to get at is what's happening each time. Well, you've got a carbon double bonded to an oxygen, and this is going to be highly polar. So an atom with a lone pair and a hydrogen will approach the carbon on the polar C double bond O. The atom with the lone pair will obviously have a delta minus on it, or it may even be negatively charged altogether. So negatively charged or partially negatively charged atoms will tend to attract to this carbon. That will enable them, if they have a lone pair, to donate that lone pair and form a dative covalent bond. Now what will happen is that carbon will now have, if it has a dative covalent bond, it has 5 bonds. So this chlorine can drop off. So this chlorine and the hydrogen atom that's attached to the nucleophilic atom will find each other and make HCl, as you can see in these two examples. So this is what they all have in common. Let's take an acyl chloride such as ethanoyl chloride. You have any atom or group of atoms which has a lone pair, in other words, a nucleophile. So the actual atom that behaves as a nucleophile must possess a lone pair of electrons. That allows it to form a dative covalent bond with this carbon. So you can see the dative covalent bond here. This hydrogen and this chlorine will find each other and make HCl. So these are the examples from the previous slide. I'm just going to take you through each one. So in each case, Nu will be a slightly different atom. So O bonded to H in H2O, the oxygen has a lone pair. That's what's going on here. In the blue example, O bonded to H but attached to an CH3, the oxygen still has a lone pair, so this is going to be methanol. So this is the blue example here. Ammonia has a nitrogen that's attached to a hydrogen, and the nitrogen has a lone pair. That's the brown example. And the green example is slightly unusual, but the oxygen is bonded ionically to Na+. So this is your CH3COO, and this is an ionic bond here. Once the Na plus drops off, a lone pair will be made available on the oxygen that's left behind. That's this oxygen here, and the same thing over here. So this makes an acid anhydride, which is this kind of structure over here. So we said earlier the hydrogen bonded to the nucleophilic atom ends up with the chlorine, and then the HCl comes off as a side product. That happens every single time. The only exception is down here. And what's left behind is a new carbon double bond oxygen containing functional group, such as the ones we looked at before. You can see they've all got a C double bond O in there somewhere. So let's try an example. If we put our template to use up at the top, this is the question we're going to try. So I'm going to do some color coding here. The propanoyl chloride that they mention here, I'm just going to pop it over on the side in yellow. And the incoming nucleophile is going to be in blue. So let's start with ethanol. So this is the product that's formed. The blue part would have come from the ethanol molecule. The yellow part would have come from the propanoyl chloride. So this is ethyl propanoate, and the functional group present is an ester. If we take phenol, this time the acyl chloride would have been responsible for this part of the molecule, the yellow part, and the phenol would have been responsible for the blue part. So this is phenyl propanoate, and this is a phenyl ester. There's no real difference between phenyl esters and other esters. It's just phenyl esters have a benzene ring directly attached to the ester functional group. So if we take ammonia this time, ammonia is the nucleophile. So the propanoyl chloride is going to be responsible for the yellow part of the molecule. The ammonia will be responsible for the blue part. So this will be called propanamide, and this is a primary amide like we talked about before. So finally, methylamine. So methyl, not surprisingly, is just one carbon. An amine functional group is a nitrogen with at least one hydrogen attached to it. So the nitrogen still has a lone pair on it. So it's CH3NH2 would be the one here. And this will be the structure. So the methylamine part would be the blue bit of the structure, and the propanoyl chloride would end up as the yellow part of the structure. So this would be called N-methyl propanamide. It's a secondary amide this time. I'm just going to quickly show you what the N-methyl part means. It comes from the fact that the CH3 is actually substituted directly onto the nitrogen. So I'm talking about this CH3 here. It's bonded directly to the nitrogen. Okay, so that takes us to the end of this short roundup of acyl chloride reactions. I hope it's helped you see what they have in common every time to allow you to predict what might happen if an unfamiliar nucleophile was to react with an acyl chloride, instead of remembering tons and tons and tons of different permutations. It's always good to try and work out the basis of what's going on, and then you can use that to apply your knowledge. Okay, as always, thank you very much, and until next time, see you soon.